every single day, across dozens of countries, in dozens of languages, in laboratories funded by governments, universities, and research institutes that have nothing to do with each other. Scientists are publishing studies on the same physical activity. It is not a novel pharmaceutical compound. It is not an emerging training protocol developed by elite sports scientists. It is not a piece of technology requiring a subscription. It is the movement that human bipedal anatomy was specifically shaped by 4 million years of evolutionary pressure to perform with extraordinary efficiency: walking. The research base supporting the health effects of regular walking is, by any honest measure, one of the most extensive, most replicated, and most methodologically diverse in all of human health science. And what it collectively describes, when you trace the actual mechanisms rather than the headline claims, is a single physical behavior touching more biological systems simultaneously than almost any other daily action a human body can perform. Before the mechanisms, a brief word on why the walking research deserves particular credibility rather than the skepticism increasingly and often justifiably applied to health research more broadly. Many health claims rest on small studies, short durations, surrogate outcomes, and single research groups that have not been independently replicated. The walking literature is different in kind. It includes prospective cohort studies following hundreds of thousands of people for decades. It includes randomized controlled trials with objective step count measurement rather than self-reported activity. It includes mechanistic laboratory research identifying specific molecular pathways. It includes neuroimaging studies directly measuring brain structural changes. And it includes research conducted across populations with different diets, different genetics, different climates, and different cultures, with consistent directional findings across all of them. When an association appears across this range of methodological approaches and population contexts, the bar for concluding it reflects a genuine biological relationship rather than confounding or measurement error becomes very high. Walking clears that bar across multiple health outcomes with an unusual degree of scientific confidence. What exactly happens to your body in the first 10 minutes of a sustained walk? The change begins before you have completed the first block. As your leg muscles begin contracting in the rhythmic, alternating pattern of bipedal gait, they immediately demand more ATP than the resting phosphocreatine system can supply, and the metabolic machinery shifts within seconds toward glycolysis and aerobic oxidation, increasing the rate of oxygen consumption and triggering a rapid rise in cardiac output to match the increased oxygen demand of the working tissue. Your heart rate begins climbing within the first minute, not because anything has gone wrong, but because the sinoatrial node has received a withdrawal of parasympathetic vagal tone, releasing the inhibitory brake that keeps heart rate low at rest, combined with a rise in sympathetic drive, simultaneously removing the brake and pressing the accelerator, producing the cardiac response to exercise onset in a remarkably coordinated way. Blood is redistributed away from organs with low immediate demand, particularly the gastrointestinal tract and skin, and toward the working skeletal muscles, through vasoconstriction in the former and vasodilation in the latter, coordinated by autonomic nervous system signals, and by locally produced vasodilatory compounds in the active muscle itself, including nitric oxide, a gas produced by the endothelial cells lining muscle capillaries in direct response to increased blood flow and shear stress. Nitric oxide causes smooth muscle in the capillary walls to relax, widening the vessel and allowing more blood to reach the working tissue. And this local vasodilation is so rapid and so effective that muscle blood flow can increase more than 20-fold relative to rest during vigorous, sustained walking. The endothelial cells producing this nitric oxide are also the cells most directly responsive to the chronic cardiovascular benefits of regular exercise. Repeated bouts of elevated shear stress, the frictional force of blood moving across the inner surface of vessels, stimulate endothelial nitric oxide synthase expression, improving the endothelium's capacity to vasodilate on demand, reducing resting vascular resistance, and contributing to the lower resting blood pressure and improved arterial compliance consistently observed in people who walk regularly and persistently. Within the first 10 to 15 minutes of a walk at moderate pace, your working muscles are also consuming glucose from the bloodstream at a significantly elevated rate, pulling glucose down from circulation, partly through insulin-dependent mechanisms, and partly, crucially, through an insulin-independent mechanism involving a protein called GLUT4. Under resting conditions, GLUT4 glucose transporters sit inside the muscle fiber in vesicles waiting to be called to the cell surface. Insulin signals them to the surface in response to a meal. But muscle contraction, independently of insulin, also signals GLUT4 to the cell surface through a different pathway involving AMPK, an energy-sensing enzyme activated when the ratio of AMP to ATP inside the cell rises, indicating that the cell is spending energy faster than it is regenerating it. This means that during walking, your working muscle is absorbing glucose from the blood through a mechanism that does not require insulin, actively reducing blood glucose concentration through a channel that remains available even when insulin signaling is impaired. This insulin-independent glucose uptake pathway is directly relevant to why walking after meals consistently reduces post-meal blood glucose spikes, a response repeatedly documented in research, including in people with type 2 diabetes, where impaired insulin signaling makes the insulin-independent GLUT4 mechanism proportionally even more valuable. And why regular walking is one of the most consistently effective lifestyle interventions for improving glycemic control, measured by HbA1c across large randomized trial meta-analysis. 10 minutes into a sustained walk, a different class of biological event is beginning, one that operates on a longer timescale and whose effects accumulate across weeks and months of regular walking in ways that are now among the most exciting findings in neuroscience. Your brain, responding to the combined signals of elevated heart rate, increased cerebral blood flow, rising core temperature, elevated catecholamines, and rhythmic proprioceptive input from the locomotor pattern itself, begins increasing its production of a protein called brain-derived neurotrophic factor, abbreviated BDNF. BDNF is a neurotrophin, a member of a family of proteins that promote the survival, growth, differentiation, and synaptic strengthening of neurons. It is sometimes described, loosely but not entirely inaccurately, as fertilizer for brain cells, because its effects on neuronal health and connectivity are as broad and fundamental as that metaphor suggests. BDNF binds to a receptor called TRKB expressed on neurons throughout the brain, activating intracellular signaling cascades that promote neuronal survival, stimulate the formation of new synaptic connections, and directly support the process of neurogenesis, the birth of new neurons, in the specific brain region where adult neurogenesis is most robustly documented, the hippocampus. The hippocampus, the seahorse-shaped structure in the medial temporal lobe, is the brain's primary site for encoding new explicit memories and for spatial navigation. And it is also one of the brain regions most vulnerable to age-related structural decline, stress-induced damage, and the atrophy associated with depressive disorders. Research by Scott Erickson and colleagues at the University of Illinois, published in a landmark 2011 paper in the Proceedings of the National Academy of Sciences, directly measured hippocampal volume using MRI in a randomized controlled trial, comparing an aerobic walking group against a stretching control group over 1 year. The walking group showed a measurable increase in hippocampal volume, approximately 2%, while the control group showed the modest decline in hippocampal volume typical of normal aging over the same period. A 2% increase may sound modest, and in absolute terms it is. What it represents functionally is the reversal of approximately 1 to 2 years of typical age-related hippocampal shrinkage, produced by regular walking 3 times per week for 12 months. This structural brain change was accompanied by measured improvements in spatial memory performance in the walking group, and correlated with improvements in BDNF levels measured in the blood, providing a direct mechanistic link from the walking stimulus through BDNF production to hippocampal structural change to functional cognitive benefit. This is not a correlation observed across a population with different habits. It is a randomized, controlled experimental finding with a known mechanism, a measured structural change, and a measured functional consequence, and it has since been replicated with consistent directional findings across multiple independent research groups working in different countries with different populations. The brain effects of walking extend beyond the hippocampus and beyond BDNF. Regular walking consistently reduces circulating cortisol, the primary glucocorticoid stress hormone, through mechanisms involving both the direct metabolic consumption of cortisol by working muscle and the longer-term effect of regular exercise on hypothalamic pituitary adrenal axis regulation, the feedback loop governing cortisol production. Chronically elevated cortisol is directly neurotoxic to hippocampal neurons. It promotes the retraction of dendritic branches and suppresses neurogenesis in exactly the region BDNF supports, meaning that the cortisol-reducing and BDNF-increasing effects of walking on the brain are complementary and partially overlapping in their protective consequences for hippocampal integrity. The mood effects of regular walking that are consistently reported subjectively and measured objectively in clinical research are mechanistically grounded in these same pathways, compounded by the acute effects of walking on monoamine neurotransmitter release. Serotonin, dopamine, and norepinephrine all rise acutely during sustained moderate-intensity exercise, including walking, through mechanisms involving increased synthesis and reduced reuptake in the relevant synaptic terminals. These acute changes in neurotransmitter availability produce the well-documented improvements in mood, reduction in anxiety, and sense of mental clarity that so many regular walkers describe in the hours following a walk. And the chronic effects of regular walking on HPA axis regulation and BDNF production underlie the more durable antidepressant effects documented in clinical trials, comparing walking interventions against pharmacological treatment and against controls in populations with mild to moderate depression. Script block 210030-00. The systemic anti-inflammatory effect of regular walking operates through several partially overlapping mechanisms, each one contributing to the reduction in chronic low-grade inflammation we discussed in earlier explorations of exercise and cancer risk, and each one relevant to an enormous range of chronic diseases in which persistent low-grade inflammation is a contributing driver. Regular walking reduces visceral adipose tissue, the metabolically active fat stored around the abdominal organs that is particularly prolific in its production of pro-inflammatory cytokines, including tumor necrosis factor alpha and interleukin-6. Each kilogram of visceral fat lost through sustained walking represents a reduction in the ongoing inflammatory signaling load that the immune system must manage. And this body composition effect alone accounts for a meaningful fraction of the downstream inflammatory improvements associated with regular physical activity. But walking also exerts anti-inflammatory effects that are independent of body composition change, operating through direct effects on immune cell populations. On the autonomic nervous system tone, we explored in the sleep narration, and through the anti-inflammatory properties of the myokines released by working muscle. The vagal tone improvement associated with regular walking, the shift toward greater parasympathetic dominance reflected in higher resting heart rate variability, has direct anti-inflammatory consequences because the vagus nerve is a component of the inflammatory reflex, a neural circuit discovered by Kevin Tracy and colleagues that allows the nervous system to directly suppress immune activation through acetylcholine signaling in the spleen. Regular walking, by improving vagal tone, effectively increases the gain on this endogenous anti-inflammatory circuit. Walking also serves as a mechanical pump for the lymphatic system in a way that is almost entirely unappreciated in popular discussion of walking's health benefits. The lymphatic system, which drains interstitial fluid and carries immune cells through lymph nodes for filtering, has no dedicated central pump. Lymph flow depends on the compression of lymphatic vessels by surrounding skeletal muscle contraction and by respiration. The rhythmic alternating muscular activity of walking, The cyclical contraction and relaxation of calf muscles, tibialis anterior, quadriceps, hamstrings, and hip flexors across thousands of steps, provides continuous compression and decompression of the lymphatic vessels running through the legs, driving lymph upward toward the thoracic duct and into the venous circulation far more effectively than sitting still allows. Poor lymphatic circulation contributes to peripheral edema, immune dysfunction, and reduced clearance of waste products from peripheral tissues, all of which improve with regular walking through this direct mechanical pumping mechanism that requires no specific exercise intensity, only movement. The effects of regular walking on sleep architecture deserve direct attention because the relationship between walking and sleep quality runs through multiple distinct pathways and produces effects measurable at the level of sleep stage composition rather than simply self-reported subjective sleep satisfaction. Regular walkers show greater slow-wave sleep, the deep, restorative stage characterized by delta wave brain activity, peak growth hormone release, and the most significant glymphatic brain cleaning, compared to sedentary individuals matched for age and demographics in multiple polysomnographic studies. The mechanisms include the thermogenic effect of exercise, producing the post-exercise core body temperature rise, and subsequent fall that mirrors and reinforces the natural temperature drop that facilitates sleep onset. They include the adenosine accumulation that accompanies sustained metabolic activity throughout the day, since adenosine, the molecular substrate of sleep pressure, accumulates in proportion to cellular energy expenditure and is the same molecule that caffeine blocks at its receptor. And they include the cortisol reduction effect, since chronically elevated evening cortisol is one of the most common causes of difficulty initiating and maintaining sleep. The practical dose question is one the research addresses with sufficient resolution to give a specific, honest answer. Meta-analyses examining the dose-response relationship between walking volume and health outcomes consistently find that meaningful benefits begin at approximately 7,000 to 8,000 steps per day in most measured health outcomes, with the most frequently cited threshold for mortality benefits sitting around 8,000 steps per day. A figure that emerged prominently from research published in JAMA by Aimin Lee and colleagues examining step count and mortality across a large prospective study, and subsequently replicated and refined across additional studies. The frequently cited 10,000 steps figure, by contrast, appears to have originated not in research, but in a 1960s Japanese marketing campaign for a pedometer. And while walking 10,000 steps daily is unlikely to harm anyone, the evidence does not specifically support 10,000 as a clinically meaningful threshold above 8,000 for most outcomes in most populations. What the research also consistently supports is that the benefits of walking are not exclusively dependent on total step count. Intensity matters independently. Research has demonstrated that incorporating brief bouts of faster walking, described as brisk walking, typically defined as a pace at which you can talk but not sing comfortably, produces superior cardiovascular adaptation and superior mortality risk reduction compared to the same total step count performed at an uniformly slow pace. The specific contribution of intensity appears to be additive to the contribution of volume, meaning that the best documented walking protocol involves both adequate daily volume and regular inclusion of brisker-paced segments, rather than treating all walking as equivalent regardless of pace. So here is the real reframe to sit with as we close this exploration. Walking is not the consolation prize of the exercise world, the thing you do when you cannot manage something more serious. It is the physical behavior most precisely matched to the biomechanical and physiological architecture, 4 million years of selection pressure built into your species. The behavior your cardiovascular system expects, your lymphatic system depends on, your hippocampus requires for structural maintenance, your HPA axis uses as its primary calibration signal, your insulin sensitivity is governed by, and your sleep architecture is shaped by. The broadness of its effects is not accidental. It is the direct biological consequence of a species performing the behavior it was built to perform. Every system in your body was assembled around the expectation of daily walking. And when it does not receive it, every one of those systems registers the absence in the same quiet, cumulative, eventually consequential way that any system registers the chronic withdrawal of the input it was designed to receive. What other daily behavior do you most want to understand at this level of mechanistic detail? Leave your answer in the comments below, and we may build the next episode directly around the biology hiding inside the habit you are most curious about. Until then, keep questioning the things you assumed you already understood, because the most powerful medicine available to most people on Earth requires no prescription, no payment, and nothing more than the willingness to step outside and move.